Okay, ladies and gentlemen, hi, welcome back. So let me try to close the shades, or at least to put down one of the shades, and then we start. So, no, it doesn't help, doesn't matter. Let us now go to the homeworks, and as you probably remember, just a second, this is the lecture, but I also have the homework here. We had a relatively simple homework, and then we can consider here in a class as a tutorial one more exercise of the same type, which I will then maybe refer to in one of the following lectures. So let us start with this very simple variant with the polymer brush. Is there anybody who did it and would like to share the solution with us?
I've done something. I'm not sure how good it is, but I did it a couple of days ago, so I'm trying to remember what I actually did.
Okay. You know, first, it doesn't matter. It is important to talk. And at the end, I will help anyhow. And to everybody, you know, somehow I thought that you would be more active because during the real classes, you know, I'm very reluctant of collecting the homeworks, correcting the homeworks. It's essentially enough that we discuss them, but in the class we can always communicate, and here we can hardly communicate. Not only that I don't see the faces, and therefore I don't see any reactions except for from Mr. Maybury. I don't have feedbacks. Even if you did not solve, it doesn't matter. We discuss. Then you think about it. Then you learn. Otherwise, I am afraid that you will not learn, although the exercises we're considering here are extremely simple. In the, you know, in the examination, there will be the variants of exactly the same exercises, but the variants, and simple questions. Okay, so Mr. Maybury, let me share the screen with you. So I will stop my screen first, and now I will announce you as a co-host stellen. And now you are able to show us what you have done.
Let me just get it onto my computer. It's taking a while.
We have time, you know. We have time. And I hope they have fixed the wireless connection. At least now it works, but who knows what happens afterwards. Okay. So, what is the idea behind? Unmute yourself.
There, sorry, can you hear me now?
Wonderful. Because when you play this, what's the instrument? Is it ukulele or it's
mandolin?
Mandolin, okay. Because I have hardly seen the rest except for the end. So okay, great, thank you. Now we can hear you.
So the idea is to consider the brush as like a collection of individual capillaries, and the distance between each polymer chain is the diameter of the capillary. And so we've got from the lectures, we've got the definition, the length of the polymer chain is equal to the number of, I can't quite remember, the number of monomers times the width of the blob or the width of the capillary.
It's not the number of monomers, because if you look at the geometry, it's the number of blobs.
Number of blobs, okay.
Yes.
And yeah, so the number of blobs times the width of the
correct
of the thing, and so here since we don't have an actual width, we've only got a density, but the density is proportional to the inverse of the width.
How do you know?
Sorry?
How do you know?
Because the density is in what do you call the dimension of the density is in 1 / centimeters squared.
Correct.
So
now look at the dimensions in your expression, d proportional to 1 divided by sigma.
So it should be d squared proportional to 1 over
d
sigma.
Squared proportional to 1 over sigma.
Okay.
Or d proportional to square root of sigma.
Yeah.
And when solving the,
I think I was confused.
The changes are not large, but they are important.
Yeah.
Okay, now let us go on. So it's 1 over sigma squared.
Yeah.
Or d squared 1 over sigma, or d is 1 over square root of sigma. Sorry.
Yeah. And so then we've defined d, and then we have, and from the lecture notes as well, we can see that n, so the number of blobs is equal to the number of monomers this time, divided by d over a to the 1 over nu.
So d over a divided by 1 over nu is what? This you get from a m to the power of nu is equal to d.
Yes.
So try to be a bit more consistent. So you have now two equations, and one is that the height, the very first, so to say, equation, the height, so to say, of the chain is the number of blobs times the size of one blob.
Yeah.
And then the numbers of monomers, the number of monomers within one blob is given by this second equation, which defines as the number of monomers per blob.
Yeah.
Okay, and then we can go on. So we have here the number of blobs, which is n divided by this, d divided by a to the power of 1 over nu, and now go on.
And since we're in 3 dimensions, nu equals 3 over 5. So 1 over nu is 5 over 3. And by continuing through this, we get h equals this. But then I didn't take into account d. I should have squared the d here.
No.
So it's
no. If you square the d in equation for h, you get meters or length on the left-hand side area on the right-hand side. So you know the theory of dimensional analysis is useful not only theoretically, but on each step of calculation. And when I see something like this, the first thing I immediately do is checking the dimensions. Okay, now it's nicer.
So yeah, so we put the square root on the sigma instead of the d,
Yes.
so that gives us sigma to the 1/5 instead of the 2/5.
Okay, but let me have a look already here. What is the dimension here in the line before the last line?
So d has dimensions of distance, of length. So
D is length, and A is length.
Yeah, and we want length in the end.
Yes, we have length here in this expression.
No, we have length to some strange power.
Correct. So where is the error?
It should be d to the 3/5.
5/3 plus 3/5 is also a strange power. Look, let's go line by line. First line, the dimension is correct. Second line, the dimension is the same because denominator is dimensionless. D divided by A is dimensionless.
Yeah.
Now you put there 1/nu, which is 5/3.
Yeah.
And then something happens. Now, where does it happen?
Is it just my arithmetic, which is...
This happens in the third line. The dimension in D is wrong. The power of D is wrong.
So that's d to the 1 minus d to the... Oh, okay, it should be 1 minus 5/3.
Correct.
Yeah.
So now let's go through and get the correct answer. And then I will show you another plausibility check, so to say, which immediately explains you why your expression for H, which you had here, was incorrect independently on whether you write 2/5 or 1/5 in the denominator. But first, let's get a correct one.
Okay.
Okay.
So then we get d to the minus 2/3. And which then gives us sigma to the 3rd instead of to the 5th here. Correct?
So what do you see here? 1/3. And I would say that this expression also does not pass the second plausibility check. And moreover, it again has a wrong dimension. So let's discuss. Let's discuss some very simple physics. What happens if sigma is so large that the distance between the grafting points is exactly A, which means sigma is 1 divided by A squared? What would be the height in this case? So what you have then is that each blob consists exactly of one monomer. You can't place anything more there. The chains are closely squeezed together.
So the chains would be perfectly straight.
Correct. And they will be perfectly straight.
Yeah. And H would be equals to n times A.
And H should be equal to n times A. Correct. Yeah. So what happens with your formula if I put sigma equal to 1 divided by A squared?
sorry, what? Sigma equals 1 divided by
divided by a squared.
I need to see it written down.
No problem. We have
Sorry?
I say no problem. We have time. We have to discuss.
I don't suppose you could do it on your tablet.
Okay, I can do it on my tablet. I think now everything works. So now let me find my tablet here. It is somewhere, yes. And let me share screen with it. And now just a second. Why? I think we still have some problems because it does share screen, but it doesn't show it. I'll try once again. Oh, now it's here. Wait, it's very slow. So it's a connection problem here, local within the building. So we have now, let me draw a picture. So this is the surface, and here we have this, so to say, I will only draw these tubes of blobs. So this distance, here we have blobs within the thing. So here are blobs. This is our model. And this guy is, let's call it L. And L is of the order of 1 divided by square root of sigma. This is what we know. And it's essentially also the size of the blob, because when we look at this geometric arrangement, then we see that they are essentially equal, or at least of the same order of magnitude. And then we say that up, it's again the
just got disconnected.
It's again disconnected. So it's a kind of local network problem which affects the wireless but does not affect the, so to say, the hardwire connection. Now let me go to my whiteboard and draw everything there. So here is my whiteboard. Let me now draw the same picture here. So this is our surface. These are, so to say, the chains, each in its virtual capillary. These are the blobs. And then we say that, you can see it, yes, wonderful. And then we say that this is of the order of the size of the blob. So D is of the order of 1 divided by square root of sigma. This is clear. Now we say that within this guy we have n blobs. so that H is N times D, we say that on the other hand, D is equal to AM to the power of nu, where M is the number of monomers per blob. And then we say that this N, the number of blobs within the chain, times M is the total number of monomers per chain. So this is essentially, together with this guy, is our system of equation we have to solve. Then your way of solution was as follows. You said that M is equal to D divided by A to the power of 1 over nu, which is absolutely correct. Then N, small n, is equal to N divided by M is equal to N divided by D over A to the power of 1 over nu. And then you, to get H, to get the height, you multiply this N with the size of the block, which means that H is equal to Dn is equal to capital N D divided by D. I would open here the powers, 1 over nu, A 1 over nu. This goes into the numerator. So the final result is N. Now you have D 1 minus 1 over nu, A 1 over nu. You see, at this stage, the dimension is okay, because this is length and this is length, so the total is length to the power of 1. And the last thing we do is to put, instead of D, 1 over sigma, square root of sigma, sigma minus 1/2. So the final result is N D sigma to the power of minus 1/2, 1 minus 1 over nu, A to the power of 1 over nu. And now we can put down, if you can see, now we can put down the powers. 1 over nu is 5/3. 1 minus 5/3 is minus 2/3. So here I will have 1/3. So what I have is then N. So let me put it down, because I'm not very good in. So this is 1 minus 5/3 is equal 3 minus 5 minus 2/3. And here we have minus 1/2, so it's 1/3. This is correct. And sigma to the power of 1/3, A to the power of 1 over nu, it's 5/3. A to the power of 5/3. Now, first we check the dimension. Length 5/3, and this is 1 over length squared, length minus 2/3. It's length. It's okay. And second, if we say that sigma is equal 1 divided by A squared, we get here sigma 1/3, A to the power of minus 2/3, it's NA. And it also passes this plausibility check. So this is the result. Now we have it. Okay. And this was a simpler exercise, or the simplest exercise. And now let us consider a slightly more complicated one, namely our exercise 2.
Actually, I have some question about question 1.
Please. You're welcome.
Could I share my screen?
First, you have to tell me who are you,
The one with the profile picture, the Qisonghu.
Yes,
Sorry,
just a second, because just a second. Once again,
Yeah.
once again, once again, once again. I lost you now. Kwesonku.
Yeah, actually, I have two
Yes,
accounts there.
just a second. Co-host
Okay.
erstellen, co-host erstellen. Now you can share your screen with us.
No, there is another one. I have two accounts in this room. One is my iPad. So
Which one do I have to take?
let me write something in there. Like,
just write something in the chat. I will open the chat. This one with a picture.
Yes.
Okay, now I have it. Just a second. Just a second. And now I will announce you as a co-host. Now you can share your screen with us.
Like, because my question is about this part.
Yes.
Like what you said before, you said like the D like to this. Yeah, but there is no exactly the relationship between them, just like the permutation
The problem is here very simple. All these considerations, which are based on scaling, they never give us the prefactors. There is a general belief that they are of the order of unity, which means that, let's say, it may be one, but it may be three.
Oh, so the problem is scaling, yeah.
So it's only scaling. You will never get, by these considerations, much more than scaling, because you also do not know, for example, what is standing here in D is equal to A m to the power of nu. They're already there. They might be a prefactor. So therefore, we refrain from considering all the prefactors here. Normally, if you are only interested in the functional dependencies, you will never, essentially, if you are only interested in functional dependencies, you will never make a mistake. But at the end, of course, there is a number prefactor here.
Yes, that's my point.
Yes, which you do not know.
Okay.
And I can tell you a story if you want, but let's do it later.
Okay.
About my diploma defense, which is already, it was 81, which means it's 40 years ago, 39 years ago. And then I will tell you a story.
Okay.
What happens if you calculate the prefactors? But, yes, but still, the functional dependencies we get are correct.
Yes.
And the dimensions must be correct. The only thing we do not get are the prefactors.
Sure. Let me stop.
Professor, can I ask a general
Sure,
question? I mean, it can be like simplest question maybe, but for example, as you said that this is easiest problem, but for me, I was like lost in between. I could understand that we need h is like the end-to-end distance, but when it says that density and on the surface the sigma points is points divided by centimeters square, or the densely packed bulbs. I just want your suggestion or advice, like how I should process this information. Like I don't know, or I get stuck in between solving the problem. That's why I cannot go ahead. Like I cannot translate these into equations, or I am struggling there.
So first, do you understand what is the density of points on a surface? I simply want to figure out where the misunderstanding starts. If you consider important and complicated problems, you go step per step. And if you cannot solve, you have first to figure out what, exactly at what step, so to say, the non-understanding or misunderstanding starts. So now we're looking at our surface from above. Do you understand what the density of points there is? Of grafting points?
Points as in like I can imagine that we need to imagine like there will be like instead of spheres we need to consider like a circle, and in the square box I will just see circles with the points will be the center of the circle, and something like this I can imagine. But it will be great if you can just tell me or something.
I don't understand what to tell you. This is my problem. Therefore, I ask.
Okay.
I never ask the questions I am not interested in. So let us look at first only at the grafting points, and let us consider some typical configuration, and then consider the simplifications we do. So now imagine you start growing your polymers from their grafting points by some chemical process. It doesn't matter. So you have, these are the grafting points. I put them at random first. So here they start to grow at this process. We say it doesn't matter how they are distributed indeed, because we're only making the estimates by the order of magnitude. But if I have now a huge square of the size L times L saying that your sigma is something, means that the number of points, just a second, is sigma times L squared. Yes? And the typical area per point is then n points divided by L squared is 1 over sigma. This means that if I consider, now it doesn't matter how I do it exactly. There are exact mathematical procedures to say what is the tessellation of a plane generated by the points. But imagine we consider all parts on the plane which are closer to one point to another, and say these are the areas pertinent to the corresponding points. So I don't really draw a real Voronoi tessellation, but let's say this is a neighboring area of this guy, and this is a neighboring area of this guy. And the typical area of this domain, which lays closer to this point than to any other point, is 1 over sigma, simply from dimension.
Okay.
Question, do you get this?
I think yes.
Yes. Then what if this is the area? And if the points are, if the domains are not, there is no reason for them to be like needles elongated and whatever, they have the similar dimensions in each direction. What is a typical dimension of the domain? It's around square root of its area. So the typical dimension, I will call it d small. D small is of the order of 1 divided by square root of sigma. Yes, in our discussion which we used, we simply said, okay, let's imagine that the points are situated on a square lattice. Then this of the order of will be exact. Yes, because this is exactly the domain, and its size is equal to the distance between the neighboring points. Therefore, the area is exactly the distance between the neighboring points. If you consider other lattices or other tessellations, which means the somehow cutting this plane into neighboring domain of each point, there will be other prefactors, but the dependence on sigma just on the reasons of dimension will be the same. A characteristic length, a characteristic distance between the 2 points is proportional to inverse square root of the surface density of the points.
Okay, thank you.
Do we have to consider something else, or now it gets more or less clear?
More or less clear. Yes,
Okay.
I can think on this.
Think on this. And always check yourself by checking dimensions and going to limits. These are the two standard ways to avoid mistakes. Okay, now let us go to the second exercise, which was a little bit more involved. Who wants, let me open the chat. Who wants to show us the solution or to discuss the solution with us? If something gets wrong, I will help, but I don't want to give you a solution without discussion.
If nobody wants to share, I can share.
Share.
Minutes.
Well, no problem. We have time. We have time. You know, the less I talk, the more I smoke. It's not healthy, but I am enjoying it also because I am the only person on the whole half of a story of a large building. Okay.
I don't know, like.
Wonderful. We see something. So
Yeah.
start explaining.
I don't know, where is it? Oh. First, I think there's something wrong with my solutions. Just like, first, like, this model is like when you look at it from the front view, it would be like this way. Like, so the diameter of our balls, each balls, like is D, and is it? I forget. And for one balls, the D should be equal to the length of the segments in each balls. The small n means the how much the segments in each balls. So it's the same the formula for this one. So from this one we can get this formula.
Okay.
And then let's consider if we look at from the top view, it will be like it will be like this top view. Like it will be like this way because it's like between two planes, so it can be like you said, like is self-voting chains. You can go to anywhere. And because in the question it says the A is which is D, like the.
It's proportional to D. D is proportional to AN. So I don't understand the sign. It's much smaller. Why do you say this?
Yeah, because if we say this means the polymer is much bigger than the distance between the.
So first tell me what is what? The notation. What is the notation? Because just, you know, when you solve the problems, and here I'm sitting and all the problem solver, which have solved many problems from different domains of science, some of them, of course, wrongly in my life, which is long enough also to get many wrong solutions. But first, when you start, especially in these simple exercises, try to invent a consistent set of notations. So now what your notation is, if you can write here, and you definitely can on your PDF or whatever it is, first define the letters. D we understand because D is drawn.
Yeah.
Now A we understand because A we always use for only one thing. It's the size of a repeated unit.
Mm-hmm.
Now, there is here capital N, and then there are some words which I do not understand. I cannot read them, and probably other people also cannot read them. I read it as N is a super leg, and I don't make any meaning of this super leg. So
okay,
what
yeah,
is capital N?
It's been a long time for me. Let me think. I make all the letter in there. It's like the small n means the segments in one boss, and the
First, it's the following. It's not a ball, it's a blob. It's
okay, blob. Okay, sorry.
It's not blob, it's blob. It's wonderful. Okay. So you just, this is again something I don't quite like, because typically by capital N we denote the polymerization degree, the total number of monomers. But it doesn't matter. Okay, you say you have capital N monomers per blob.
No, it means how much balls in hold the polymer.
You mean this is the number of blobs?
Yes.
Okay. Then how do I make sense of the equation which stands to the left from upper? R is equal to NA, because I am going through your sheet of paper. Now imagine you have submitted it for the correction. Yes, and I will have to correct it. I will immediately write, I don't understand the word, and return it to you with 0 mark, but everybody is happy that I'm not doing this. Yeah. So how do I have to understand this equation?
Yeah, I think that's my problem. Let me try again. Like I a lot bit forget how I get this solution. So far, I don't know this equation. Later, maybe I will remember it. I forgot.
Okay, let's go on.
Yeah, first, like it's between two plates. So the distance between two plates is D. Yeah. And it also can obviously say it means the diameter of the bulbs.
Is
right?
D. Correct.
Yeah, it's D.
Correct.
Yeah, so
because blob is exactly the size when you start feeling the constraints. And this is the distance between the plates. Wonderful.
Yeah. So second step is if we change our view, like we look it from the top, like we will go through.
Correct.
These things, like because it's super big, so we can look it like the safe wording chains.
Correct.
Yes, so we can use this formula.
Why do you use this formula?
Because this formula means the end-to-end distance of the two-dimension. Oh no.
Oh no.
Yes. No. Sorry. It's not this one.
What is the Flory exponent for a two-dimensional polymer chain?
I forgot. Anyway, it's not 2 point. Anyway, is another number. It's not 1/2.
But what is the Flory exponent? How did this 3/5 came to play?
Let me check a little bit. Forgot.
Okay, let's go back just a second.
Okay.
Stop sharing your screen.
Okay.
And let me, for a second, to share mine. For this, let me first open something. Just give me a second. Because I want simply to go to the corresponding lecture. Just a second. I'm here. I don't disappear.
Yeah.
And I have a hardwire connection to the net. So now let me come back to Zoom and share my screen with you. For this, I have to close this and to share my screen. So this was lecture about the Flory exponent. And here we made this minimization of the free energy, and we obtained the result for the Flory exponent, which is nu equal to 3 divided by d plus 2. So
Yes.
in 2 dimensions, the chain has the Flory exponent of 3/4.
Yeah.
Why is it self-avoiding, this chain of blobs? This is because the blobs do not want to intersect too much with each other. You need to perform work to press the blobs into each other. This work is not very large. This work is not very large, but still it is there. So we have a self-avoiding chain, and it is larger than a simple random walk chain, for which nu would be exactly 1/2. Now you can share your screen again, and we go on.
Yes. So because of because of this step, I was wrong. So the calculation is wrong. The formula is wrong.
Does anybody have a correct calculation, or you want to continue and we get it correct together?
If anyone has the correct one, I would like to switch.
Does anybody have a correct one?
Oh, I get an answer, but I don't know if it's correct.
Okay, I think you can share and we will see.
Yeah, I have to announce you. You first stop your screen sharing. Yes? Good. Now I have. So who is speaking? This is the question, because
Fernanda.
Fernanda.
Yes.
Now I will give you the co-host rights, and you can show us your screen, your solution.
Okay.
And it doesn't matter whether it's correct or wrong. We
Okay.
simply want to discuss. We don't yet see anything.
Yeah, I am opening.
Okay. Great. Now we see something. This is very nice. Can you make it a bit larger? Because I have a relatively small laptop and I didn't take my reading glasses into the office. Oh, that's great. That's great.
No.
Now it's back again, small again. No, just type Control plus, or you can move it here, but okay, it's okay. It's okay. I can see. I hope everybody can see. Wonderful.
Okay.
Now, what I like here is first this idea to define the notation.
Okay.
Which was missing in the previous case, and I strongly recommend always to define the notation. Wonderful. So now explain.
So I started with the model of self-avoiding chain, self-avoiding wall. It
Yes.
says that the length, the end-to-end distance, is defined by the number of blocks per the diameter of the blocks, right?
But this is wrong.
This equation?
Yes. It's okay for the capillary, which is a one-dimensional self-avoiding walk. But you are in 2D. And in a self-avoiding walk, look, once again, R, which is the root mean squared end-to-end distance, goes as n to the power of nu times, let's say, A or D. This is the size of a block now. This goes to be D. But this nu stays, and nu is equal to 1 in a capillary, because your chain can only grow in one direction. It is d divided, it's 3, d divided by d plus 3 in other dimensions, which means it is 3/5 in 3 dimensions, and it is, no, it's wrong. It's wrong. I myself have forgotten the formula.
3 over d plus 2.
3 over d plus 2, sorry. Somehow I reverted it, d plus 2. And here it will be 3/4 in d equal to 2. Look, they are decaying with the dimension, and in d equal to 4, you have this classical result of 1/2. The chain is ideal. In d equal to 4, you don't have non-ideal chains.
Yeah, somehow I consider this Fleury index at the end of my equation. So
Yes, now let's now share the screen again.
okay.
Let's have a look.
Okay, so somehow I started with this equation, and then relating with the Fleury index, we know that the n depends on the dimension and the diameter and the length of the chain.
Correct.
And the segment length.
Correct.
So this is a dimensional quantity.
Yes. And this is the same as in previous case, which Mr. Maybury did. And this is now fully correct. It's wonderful.
Okay. So then I made a rearrangement in this equation to have this relationship between the n and d. So basically, I both sides to the power of the Fleury index, so I get this relation.
Okay, this I understand.
Yes. Then, as the problem says, we have to consider that the diameter of the block is too small in comparison with this product here. So basically,
just make a break and let me ask you why this additional condition was put in the exercise. What would happen otherwise? What would happen otherwise? Why do we need this?
because somehow we can approach this to a Hooke's law.
I didn't quite get it acoustically. Could you repeat, please?
It could be related with the behavior of the polymer, like the and spring, like the Hooke's law. I am not sure.
What would happen if D, this your D, is larger than A capital N to the power of nu? What would happen in the opposite case?
We have one big block.
There will be essentially, either you can say that the chain will form a single blob, but essentially the chain will simply freely swim between the planes.
Okay.
It would not separate into blobs, and it would not form a whatever non-trivial configuration. Why does it have to? It simply swims there in between, and that's all.
Okay.
So this was the only reason. Now, wonderful. This is correct.
So I consider that the exercise says that the diameter is smaller, much smaller than this product of here.
Yes.
So basically, in the relationship, if we have something very bigger divided to a small quantity, basically we can approximate this value to just this product.
Okay.
So I made this approximation, which also it is important to notice that it is adimensional because here we have centimeters, then we have centimeters, but yeah, the D quantity disappears.
Wait, this is all wonderful up to this place where you suddenly get a dimensional number small n because you have lost something.
Oh.
And the final result also doesn't pass the dimensional analysis. Without any plausibility checks, it simply doesn't pass the dimensional analysis.
Yeah, I see it.
Mm-hmm. Okay.
Yeah, so yeah, that is what I have the answer.
Okay.
Like I replaced the in n value in the equation, and I have this relationship, but yeah, the dimensions doesn't.
So there are two mistakes there, one at the beginning and one in between. And, you know, if you want, is there somebody else who wants to show us something, or you want me to show you part of the solution?
Yes, that would be great.
If that will be great, okay, then stop screen sharing. And since we have very unstable connection, I will do it on my whiteboard. And you can look on my whiteboard. Now I will only, okay. So let me remove everything here. And I will only put here two things. Nu 3, this is in 3 dimension, is 3/5, and nu 2 is 3/4. 3 over d plus 2. Now, let us define again the corresponding, just a second, I will remove the pin videos because I would like to see myself whether it is possible to see what I am writing. So, okay, I have these two news, whether you see them or you don't see them, I don't know. Now, let me define. So N is the total length of the chain. total number of monomers. N small is the number of blobs. M is the number of monomers per blob. Now what I know is that the size of the blob is D, and this means, as you correctly said, as that D is equal to AM to the power of nu. Which nu? Nu 3, in 3 dimensions, because the blob is living in 3 dimensions. Now, as again, we already discussed, if we look at everything from above, through the, let's say, glass plates, the conformation of the chain is like this. These are the blobs, and the chain makes a self-avoiding walk of blobs. In what dimension? In 2 dimensions. Because it doesn't have this vertical degree of freedom, which is restrained by the plates. It's like this. If I look from the side, this motion is restricted. Is this clear? So nobody says, I assume it is clear. Now let me go on, and the rest is essentially very simple. Now, just a second, because I'm looking at the screen. Now I remove the pictures, and what I say is then that the mean end-to-end distance of the chain in this 2-dimensional configuration, this is what I'm looking for, is the number of blobs, or is D, I will write it exactly in the same manner, the numbers of blobs to the power of nu 2. Is this clear? These are 2 equations. So this will be 1, this is 2. And the third one is essentially the connection between the both. Namely, N is equal to capital N divided by N. This is 3. Do I have to explain anything else on these 3 issues? Did everybody get it? I don't see any. Okay. Now the rest is really trivial because it's only the calculation. So in order to calculate this, I need this, M. M is given by this equation. So M is equal to D divided by A to the power of 1 over nu 3. And this is exactly what we did also in the first exercise. This means that small n is equal to capital N divided by M is equal to capital N divided by D to the power of A 1 over nu 3, which is capital N A to the power of 1 over nu 3 divided by D to the power of 1 over nu 3. Now we have the number of blobs. And now we have R, which is equal to D to the power of nu 2. So R is equal D, this guy, and A 1 over nu 3 divided by D to the power of 1 over nu 3. to the power of mu2. And now we collect all the powers. For this, I use the chair because I am very lazy. So, now we collect all the powers. What are the powers of d? D to the power of 1 minus mu2 over mu3. Minus because this d was in denominator. What is the power of a? The power of a is mu2 divided by mu3. And what is the power of n? It is mu2. First, already at this stage, I see that the dimension is correct. Because this, whatever mu2 and mu3 are, this is length 1 minus this guy, and here length plus this guy. So it's length to the power of 1. At least up to here, it's improbable that I have done a mistake. And now I put the numbers. mu2 is 3/4, and mu2 divided by mu3 is 3/4 divided by 3/5, which means this will be 3 and this will be 5. So it's 5/4. Now let us have a look at what happens. So what we get if we substitute the numbers, I will take the black marker, I will get. So it's 5/4, 1 minus 5/4, it is minus 1/4. D to the power, up to the prefactor, to the power of minus 1/4. Here I will have a to the power of 5/4, it's constant, and to the power of 3/4. Now, it is clear that the number of blobs is proportional to the number of monomers. The more monomers you have, the more blobs you have. And this means that the dependence here, which is the linear dependence on the number of blobs, translates into linear dependence on the number of monomers. But now, essentially, we can also make a plausibility check, which is here very simple. What the dependence on D in principle should be. We can at least understand that this power should be negative. Why? What happens if you squeeze the chain? What do you think? Will the end-to-end distance grow or decay?
It'll grow.
It will grow, yes. Because if they are far, there is no necessity to separate into blobs. If it is fully squeezed, it will be just like in a two-dimensional random walk. So if you put here, instead of dA, it should be a 2D result exactly, with a to the power of 1 and to the power of 3/4. So it does pass the plausibility check and the dimensionality check, so it's probably correct. And here we can stop. Now, since tomorrow you will get a new homework, I will give another homework on a picture of blobs, which will be a bit more complicated, but only a bit. Because in these two homeworks, in these two exercises of this homework, the situation was such, essentially I thought we can discuss it now, but since you will probably not solve it in the rest 20 minutes, and I don't want you to show a solution immediately without discussion, I will give it as a homework. And the idea is to consider a self-avoiding chain in a pore, where the pore is much larger, of course, than the total volume of all monomers, but smaller than the unperturbed size of the chain. And there I will pose a homework with some hint, and you will solve it, and then we can discuss, because I see that you still have difficulties with the picture, or some of you have difficulties with the picture. And what one definitely needs to do is this kind of checks, looking in the limiting cases, looking into the dimensions of the corresponding results. So I think, you know, we have quarter an hour, but let's stop here. It doesn't matter. And then next time, maybe our discussion will be longer, because there will be an additional homework, and we'll see. But anyhow, we will continue our discussions tomorrow. Are there any further questions? If somebody wants to put a question, now is the best time to put a question before I leave the meeting. I don't see any questions, so ladies and gentlemen, guys and girls, see you tomorrow. Enjoy the rest of the day. Bye.
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 Good afternoon.
Bye. Thank you.
Bye. You're welcome. See you tomorrow.